Hi everyone, I am Sean from Carnegie Mellon University. So today I will introduce a new way to detect and analyze network traffic and identify attacks. So let's begin. So network traffic is increasing day by day, and more users use internet every day, so it's crucial to do a good network traffic detection. You can not only know what's your user's preference. Do your users like to listen to music, or do they like to watch movie? So according to that information, you can manage and improve your network resources. And analyzing network traffic is a very important part of preventing attacks and intrusions. So there are different kinds of data. Network traffic just matches the 3 V's of big data. So they are high volume, high variety, and high velocity. High volume. For a small network operator, terabytes of data generated every day to log all the users' activity. We need to find a fast way to analyze all of those data. High variety. Different user loves different kinds of surfing type. So we need to deal with all kinds of data. Our detection method need to be general enough to detect even the slightest attack among those various kinds of traffic. High velocity. There are more and more users using the network, and it will not decrease, it will just increase. Network is spreading faster than ever. We need to leave enough potentials for our method to detect attacks. So here is our way to deal with network traffic. We use feature selection to reduce dimension. We use map reduce to parallelize the analytics process, and we generalize our method to deal with all kinds of various of data. So in this way, we can handle the network traffic just in seconds. Here, I want to introduce to you our dataset. It's a very legacy dataset. It is generated from 1999 KDD Cup. It's a data analytic context, and in that year it provides a detailed dataset of 7 weeks of real traffic. That's amazing. And it contains 500 million records, and the features are also very good. There are 42 features, and it contains not only normal traffic, it also contains denial of service DOS, user to root, U to R, remote to local, R to L, and probatex. It seems that we had a lot of data to analyze, but where shall we start? So here, let's take a glimpse of the record. We can divide all the 42 features into 4 categories. The red ones are the most basic features of a TCP connection, like its TCP or UDP and its protocol and the destination. The green part is the content features of TCP connection, like the bytes sent to hosts and sent from the host. The purple one are the time-based network traffic features, like how many times it has attempted on login, or how many files does the guest create in the last 2 minutes. And the last blue part is the host-based network traffic features. This record is normal in our case. So here is the NASL dataset, because many researchers found out that in the original KDD dataset, there are lots of duplicate data, and one of the researchers tried to use many algorithms, 21 algorithms, with its default parameters to test it, and the accuracy of all these 21 classifiers ranges from 85% to 99%. That's very high, but since it has a lot of duplications, the classifier will bias to the duplicate records, and it cannot be working very well in real life. What we use is the NSL dataset. In this dataset, not only the duplicated data are removed, but also all the data, if they can be both correctly classified and all of the 21 predictions are right, it will be labeled as easy and be removed from the KSL21 dataset. And as we can see from the bar chart, you can notice that the y-axis is in the log form. In fact, the top 3 kinds of labels are Smurf, Neptune, and Normal. These 3 labels contains nearly around a million instances, and the 4th label only contains 10,000 labels. So that's a big difference. What we want to do is, if we mix all kinds of labels together, we will never avoid the bias towards the normal, Smurf, and Neptune. So we decide to first classify the normal one from the abnormal one, then classify among these labels that which kind of attack is this record. Based on this thought, I proposed a way. So here is a structure of the big data analysis system. What we have is the training data. The training data, when we get the training data, we ask the experts to label them. Then we get labeled training data. Using some feature selections and other pre-processing methods, we can build our classification model using decision tree, naive Bayes, random forest, or k-nearest neighbor. After we build our model, we can get new traffic data, do the same pre-processing, and we do not need to train the classifier again because we already have one. We can simply apply this classifier to the testing data and classify each of the traffic data into 5 kinds of events. So here I proposed an algorithm. So previously a lot of papers have discussed about a single way to classify all of the data. Some of them do not have a very good result because one kind of algorithm has its own limitations. It may not be applied to all of the data. So here is our algorithm. After some feature selection, we first classify it as normal and abnormal. If we think it's normal, then we just label it as normal. If we think it's abnormal, we send it to the attack classifier. In this attack classifier, we can label each of the record to 4 kinds of attacks. Then we merge those 2 labels together and produce the final label. So after we got the data, we must do some pre-process because the data has 41 dimensions. It's so high and it will significantly slow down the processing. What can we do? We can perform some principal component analysis or feature selection or model extraction using k-means as well as normalization. Here, I have tried principal component analysis, but I think principal component analysis is more suitable to perform on numerical data. So since a lot of data in our dataset are categorical, if we just simply change it to numerical, it cannot work very well. So after I tried to do some principal component analysis, I just give it up. Besides, several papers also point out that principal component analysis does not perform well on this dataset. So I changed to feature selection. As we know, some of the features in this dataset varies little, so it does not help very much to analyze the data, so we can just throw them away. But here is the question: which features should we use and which features shall we throw away? I try to use information gain to select 21 features out of 42 features. We can also use model extraction, which I choose in some of the methods to extract a template or a model for each type of a text. We can just simply calculate the similarity between the template and the real data. If it's similar enough, then we can safely classify it to certain type. And the last one is normalization, because the scale of different features are usually very different. If we simply use the Euclidean distance on the old dataset, some of the features are severely biased. So we need to do a normalization first, then we can continue to apply other methods. So the first level of my classifier is to classify the normal and attacks. First, I choose to use random forest to do this binary classification, and since we have several datasets, let me explain it one by one. Here is the training. For the training part, I use the training set provided by NSL dataset. You can see that the accuracy of training is very high, but the other test sets like NSL21, it only contains that the most difficult records in KDD dataset, and NSL4 contains all datasets except the duplicate data. You can see that the NESL21 dataset caused a pretty low accuracy for around 60%. Notice that it's a binary classification, so this result is pretty low. For the other datasets, we can notice that the most easy one is the one provided by KDD. It's the original test set, and the random forest can perform about 92% accuracy. The x-axis is the number of trees in the random forest. As we can see that with increase of the number of trees, the accuracy remains steady. That means that increase the number of trees cannot improve accuracy. Commonly, random forest is used to reduce bias. With the increase of trees, its bias became low. But in this case, I think because we already performed feature selections, there are relatively few features in this dataset, so the bias does not occur. The next way I tried is to first use k-means to generate several templates, and for all the test set, I use one nearest neighbor to classify it. This chart is quite interesting. You can see that with the number of templates increase, the accuracy of the dataset is pretty low. For the training set, it's pretty low at first, then rise to a normal level until it reaches 1. I think it's because the more centers of k-means, the more similar of the centers to the training set. So the accuracy should be growing. But it's very interesting that the NSL20 dataset is pretty high at first, but slowly dropping down when the number of centers decrease. I think that's because the NSL20 dataset is distributed differently from the training set. So at first, they can be compatible with each other, but with the increase of model, the model tends to overfit the training set. So That's a very interesting phenomenon. You can see that the green line is also increasing with the number of centers increase. I think that's because the NSL4 dataset is similar with the training set. Centers both fit very well. The last method I choose to classify the normal and abnormal data is to use decision tree. In decision tree, I try to adjust the size of minimum buckets, but it does not influence a lot. And for the full dataset, you can see that the NSL20 dataset is still wandering around 60% accuracy. From this experiment, I also learned that a high training accuracy does not necessarily represent the testing accuracy, because as I previously mentioned that the networks varies a lot. So what you get in test set may be very different from the training set. You must have this ability to deal with it. So let's continue to our second level. In our second level, we need to classify the abnormal data into four categories. The first method I choose is to use naive Bayes. Unfortunately, it produces a pretty bad accuracy, and we can see from the confusion matrix that we are not doing very well on R2L data. Actually, we classify nearly half of the predicted R2L data are actually DOS attack. We also predicted a lot of R2L data as U2R attack. I think that's because the assumption naive Bayes made is that each of the features are independent, but in reality that's always not the case. So the performance and the accuracy are both very low in this case. And another method I use is the same as first layer, but for the first layer we use binary classification, but for the second layer we use multi-class classification. We choose each of the type to generate 5 centers for each type, and for each testing data I compare the data with existing centers and which one is the nearest to this record. I choose. I classify this record to be the nearest centers type. And you can see that it does not work well either. I think that because the many types of networks are just mixed together. It's not easy to separate them using centers or templates. So in this case, you can see a lot of probe attacks and RTL attacks are classified as DOS attack. Maybe that's because there are so many DOS attacks and it just scattered along the distribution and it's everywhere. So it has a higher chance to classify a new data point as DOS attack than any other class. So how can we use Hadoop with our previous analysis? Here is what I did. First, I trained a model on local machine. Then I saved the model as a R data file. Basically, we can upload it to the server and load it when we run the distribution. Since the model is already generated and do not need to be adjusted, we can just use it to classify all the test set. And since each record of the test set are not related to each other, we can just do an embarrassingly parallel process to speed up the process. So for our model, I choose to implement the k-means and one-year stable on Hadoop. What I did is to find the centers of each type. Here I choose k to be 5. So for each kind of attack, there are 5 centers for this attack. I store all of the centers into file and upload it to the server. Then load it again in the mapper. So when I process each of the record, I calculate the distance between it to each of the centers and find the minimum point and assign the type to this test data. In the reducer, I output into a file. Besides all of the attempts I mentioned above, there are some papers that conclude specific rules for a specific type. For example, one of the papers analyzed the features of with client and with master attack, and concluded a result that with client cat have does not have too much traffic from client to host, but many traffic from host to client. And with master attack to that exactly the opposite. So using those rules, we can add more layers to my classifier to make the result more accurate. I want to mention that using the original KDD, we can also achieve about 90% accuracy, but I think that's not representative because there are duplications and the redundancy. So I decided to choose the NSL dataset. It turns out that this dataset is very difficult and we must do a better job in the first layer, because if you classify the label as wrongly in the first layer, it has no second chance to be classified right in the second layer. So the overall accuracy of my final classifier is around 40% because the first classifier did a pretty bad job and the multi-class second layer classifier is not doing a good job on the harder dataset. But I think that's worth a try. Thank you for all your patience, and please contact me if you have any questions.